Hello, class. I'm actually doing a lecture at night. I'm going to try this because actually I can keep the windows open a little bit and keep the lights on. I have been going over this lecture. I'm not sure. Oops, wait. Oh, there you go. See, I start off. Just a second. Let me get my timer. All right. I am back again. And I've got the timer on. So I can find out, where I am, because this lecture, I think, might be 1.5 lectures, depending upon how we move through the first, example that I'm going to look at. We're going to be looking at moments. Originally, I thought I would take you straight into three-dimensional, moment calculations and stuff, but then I went back and looked at some of the things and I thought, oh, that can't possibly just move right into that. We've got to get free body diagrams out of the way. We've got to get, coordinate system transformations out of the way. And so I came up with an interesting little problem. Let's say that I've got a shaft here, right? Some type of machinery, right? So some type of machinery, and it's got a lever, and that lever comes from the center of that shaft up about 2 meters, right? Now it's coming up. Let's just get that angle right too. So this angle that it's got right here, I'm going to say is theta, and I'm going to say theta equals 60 degrees. All right. And the length of this from here to here is going to be 2 meters. Now, someone has placed a torque on this lever by going to the end of these top 2 meters and hanging a weight, right? Hanging a weight from that. That was supposed to be straight up and down. I don't know why it doesn't look straight up. Yeah, I guess it is straight up and down. Anyway, it has hung a weight there, and that weight is 100 newtons. Right? Not very much, not a very heavy weight. But because we've got such a long lever arm here, it's going to create, an interesting moment around that point right there. Let's call that point, this point right here, right in the center, we'll call that point O. Okay? And I can call this point up here, I don't really have to, I guess we have to refer to it because we've got to come up with a distance vector, don't we? So I want to look at this in 2 ways. I want to look at it this way, where we're thinking, right? I'm going to draw 2 coordinate systems now. We're going to look at it this way, where we're thinking of this as the y and this as the x, right? And of course, we would do that there, and we would also do it up here. We would have a parallel system when we were breaking the forces down too, wouldn't we, right? Because that's what we did in the last problem when we were looking at the flange that was connected to the brick wall. We took the coordinate system and we figured out what the forces were and their force components in the x and y directions. And then we also, used that same coordinate system when we looked at the flange on the wall and to figure out what the distance vectors were, right? In both of those 2 cases. Now, I'm also going to do the problem where instead of looking at that as the Cartesian coordinate system, which seems like the natural choice, doesn't it? It seems like this would be the natural choice that we would have for the Cartesian coordinate system there. But in the second way that I do this problem, I'm going to use this as my Cartesian coordinate system, right? And so this will be my x, and this will be my y. And of course, if I do it there, I'm going to have to do it down here too, aren't I? Where this would be my x, and this, the actual thing, would be my y. So you see the two different coordinate systems that I'm using, and of course they're rotated. One is rotated 30 degrees to the other one, right? Does everyone see that? How I've rotated? I've taken the y here. The y is now gone over here. This is 60 degrees. That's 90 degrees. So this would have to be 30 degrees, wouldn't it? So I've rotated one of the two coordinate systems by 30 degrees to the other one. We're going to solve it using either of these two, or I should say each of these two independently. It's going to give us the exact same result as we would assume it would be, that it would give us, right? All right, so the first one that I want to do is just this, normal one that we've got here. So if I was to look at that, I would say that F, right? If I'm going to actually write F, I would say that F is minus 100 newtons in the J, or the Y direction. I use J hat, of course, because I'm writing a vector, so I'm using the standard engineering notation for writing vectors: I hat, J hat, and K hat. And then let's figure out what the distance is then here. And if we look at that, we can see that I would have to go over. Let's just drop this down so that we can see our right triangle here, right? Everybody can see that that's a right triangle. I've got a hypotenuse of 2 meters. So I can very quickly figure out that this is going to be at 60 degrees. This distance right here is going to be 2 meters divided by 2. So it's going to be 1 meter. And 2 meters over there. Just a second. Sine of 60. Oh, I forgot to turn it on. Sorry. 2 times the sine of 60. That gives me 1.732, which would be the square root of 3, right? Everybody probably remembers that. Okay, so we've got our two distances there, and so we could say that our distance, and remember what our distance for that moment is it's going to be from O to A. Always the distance from the location you're summing the moment about to the point at which the force is being applied, right? So it's going to be 1 meter I hat plus 1.732 meters J hat. And I think everybody can see that really, the only thing that we're going to get here is R cross A, because if we look at the moment, right, about O, and it's R cross F, if I have 1.732 meters J crossed with minus 100 newtons J, well, J crossed with J gives me nothing, right? Gives me 0. So the only thing that we're really going to have is 1 meter I crossed with minus 100 newtons J, which is going to give us minus 100 Newton meters K hat. Now, why did it do that? Let's just draw this up here. I love to draw this up here. I think this is one of the things that saved me when I was a student at Notre Dame. IJK, and of course it's I cross J gives me positive K because we're going in the direction of the arrow, right? So that would be our moment that we would figure out if we were using that system. Now let's not use that system. Let's use a system. Let's say that this other system benefits us a little bit more, right? So we now want to look at what the force is. So this would be with I'll write green. In fact, why don't I write it in green so that you can remember that it's with the green coordinate system that that we looked at with the first one. And now what I want to do is I want to look at a transformation of the coordinate systems, because it might be more beneficial, right? Maybe if I transform the coordinate system to another place, it would make figuring things out a lot easier. Sometimes that's true. So let's do that. Let's just see if I switched these around. First of all, I think that everybody can see that if I did switch this around, what would be the distance, right? This would be my 0, and my distance now from O to A would be plus 2 meters J hat. Does everyone see that? So instead of it being this, it's really this. But what is my force now, right? Under this new configuration, my force is going to be positive x, negative y. And what is this angle right here? I think everybody can see that that angle is going to be theta, right? So 60 degrees. So F is going to be, if we look at this, this is going to be 60 degrees. So it would be cosine, right? Cosine of 60 degrees is going to be this distance here, and sine is going to be that distance there. So first thing we want is we want 100 newtons times the cosine of 60 degrees, right? I hat, and then minus 100 newtons times the sine of 60 degrees, J hat, right? Now let's cross multiply those again. Let's find out what the sum of the moments are about O. Well, 100 times the cosine of 60 is going to give me 50 newtons I hat, and then minus 86.6 newtons J hat. Does everyone see that? And of course, if you can do it yourself, but it'll come out to that. And so when I sum these moments, the J crossed with the J crossed with the J is going to give me nothing. But the J crossed with the I, and remember now I'm going J cross I. J cross I gives me minus K, doesn't it? That's right. J cross I gives me minus K, so I get 100 Newton meters. But then what I get is J cross I, or minus K, so the minus comes out front and the K goes back there, right? So there you go. It doesn't matter which way we were to set up our coordinate system, we're still going to get, that's supposed to be an arrow, the same thing, right? Does everyone see how I can change my coordinate system, but it's not going to change the answer? All right. Because sometimes one coordinate system will be preferable. One coordinate system transformation, I'm still talking about transformations in the Cartesian coordinate system, would be preferable. A lot of times when you go into the future, like electromagnetic field theory and stuff, you'll see that there's other coordinate systems like spherical, cylindrical, hyperbolic coordinate systems that lend themselves to a better understanding and display of different types of electric fields and waveform patterns and stuff like that. Okay, well that was the first thing that I wanted to do today. Let's see how much, oh yeah, we've got plenty of time. So what I wanted to do after that was I really, looking at the coordinate system transfer, that's one thing I've looked at already. And then free body diagrams. Now free body diagrams is something that you should look at the various types of supports that are in chapter 3, I think it is, chapter 2, it's got to be chapter 2. I'll go back and look and make sure in that book which chapter it's in, but there are various different types of supports. I'm going to do a drawing sort of right now for a variety. And we're going to do, I want to actually work through two problems, not so much free body diagram problems so much. I am going to draw, you know, the free body diagram. Let's say that I have a car, right? Now, this is why I never went into art unless I suppose it was modern art, and I was drawing for Mr. Magoo's team. There you go. So I've got a car. I've actually got it backwards because I wanted that to be the back bumper, and I wanted this to be the front of the car. But anyway, that car is accelerating. It's accelerating to 60 miles per hour, isn't it? Okay. Yeah, it looks like it's got a fender on the front there. So it's accelerating to 60 miles an hour. It's just starting from 0, and it's going to accelerate to 16 or to 60 miles an hour. Now, it also weighs, it has a mass of 2,000 kilograms, right? It has a mass of 2,000 kilograms. We're going to be looking at several different characteristics of this car. So if it's 2,000 kilograms, then what would the weight of the car be, right? Because we know that weight is mass on the surface of the Earth anyway, times the gravitational constant, right? And I'm going to be referring to some things in this sort of example problem that we're doing that I assume are review, like the equations of motion. I'm going to just write the equations of motion down here because actually there's really just two equations. Anyway, I'll write the equations of motion down here. So the final distance traveled by, you know, something accelerating or decelerating is going to be the original distance plus the original velocity times time plus 1/2 the acceleration times time squared, right? That's one equation. Then another one is the final velocity is going to be the original velocity plus acceleration times time. Now we can put those two equations together and actually come up with another equation. Now I'll do that a little later when we get into dynamics, but I'm just saying that you know, we're going to look at these two, and these are just two equations that I'm assuming that everybody has gotten in their physics course or science course of some kind in high school. But let's look at this. I may be introducing some new topics here, but that's what we're here for, to homogenize all of you guys into electrical engineers, right? So the weight force, and I should really call it F sub G, right? It's the gravitational force, is going to be 2,000 kilograms times 9.81 meters per second squared, right? So we know that F sub G is going to be 19,200 newtons, right? Because a newton is a kilogram meter per second squared. So I can use that as a shorthand nickname term for that weight. So let's draw that on our free body diagram. I got that pushing down 19,000. Is that right? Let me just 600. 19,600. I was thinking that doesn't sound right. And then I've got these two wheels. We've really got four wheels. We could divide it by 4, but I'm just drawing it in 2 dimensions right now. So my free body diagram is going to have the front axle pushing up with 9,800 pounds and the rear axle pushing up with 9,800. Actually, 9,800 and 10 pounds on both of those, and that would really give me 19,206, wouldn't it, or 6,2. Anyway, I'm just going to keep it at 600. Where is my? There we go. Should I actually put, because I do put 9.81, right? Now I'm going to leave it like that. Let's just call it 9,800, and I'll just say that that's a 0. All right, so we've got those two pushing up, right? And what we want to know is if I accelerate at my acceleration of that car is going to be 3.5 meters per second squared. Now you're saying, wow, that's pretty fast. That's pretty fast, 3.5 meters per second squared, because the gravitational constant is 9.81. That means that if a guy was, like 100, if a person was 100 pounds, they would be pushing 100 pounds down on the seat, but then they would be pushing about 35 pounds back against the back of the chair. That would be some incredible acceleration, wouldn't it? Let's see. Let's see if it's some incredible acceleration. I have this cable twisted around. Anyway, let's see if that's some incredible acceleration, all right? Because first of all, what do we really want to know about all of this? We say that that's an acceleration, but what's that force due to the acceleration? What is the force due to? Well, isn't it mass times acceleration? Mass times acceleration. Well, the mass is 2,000 kilograms. And the acceleration is going to be 3.5 meters per second squared. So that means that the mass due to the acceleration is going to be 7,000 newtons. Whew, that seems pretty fast, 7,000 newtons. Let's use this equation that we've got down here from high school. V final equals V original plus acceleration times time, right? Because we're going to 60 miles an hour, 60 miles an hour. Let's just write that down. 60 miles per hour. What would I multiply that by? I mean, I've got to get it into meters per second, don't I? Isn't that what this is here? Isn't this in the SI system in meters per second squared? So I better get something in meters per second. Well, we know a couple things. What do I want to get rid of first? Let's say that I want to get rid of miles. So I know 1 mile is equal to 1,609 meters, right? Everybody knows that. Anybody who's becoming an engineer knows that. 1,609 meters equals 1 mile. Don't get me started on the 5th significant digit there. Because we shouldn't use it. Now we got to get rid of hours, right? We need meters per second. Meters per second. Well, hours is on bottom there, so I want hours on top here. So 1 hour is 3,600 seconds, isn't it? That's right. So 60 miles per hour equals 26.82 meters per second. Does everybody see how that works? Everybody plug that into your own calculator and make sure that you can do that. I want you to do these calculations along with me while you're watching, so that you get that. That's one thing that you don't get here that you would necessarily get in class. I didn't mean to stutter there. But you would necessarily get that in class, because I would be calling on you and you would be following me calculating all of these things out. So did I write 6? 60 miles per hour equals 26.82 meters per second. So let's just do that together. 60 times 1,609 divided by 3,600 equals 26.8166. I'll go with 26.82. All right, so I want you to do that too. I want you to calculate, make sure that I'm doing all of these things right. You can't yell at me if I'm not. In class you could, and that would be fine. But that's our final velocity, isn't it? So that's our final velocity right there. We know our acceleration. We know what our original velocity is, because our original velocity, right, is 0. So if our original velocity is 0 meters per second, and our final is 26.82, can't we find out how long it's going to take us to get to 60 miles per hour? Isn't the time that it's going to take us to get to 60 miles an hour just going to be the final velocity minus the original velocity, which is 26.82, since we started at a dead stop, meters per second. That's our final velocity minus our original velocity, divided by our acceleration. And what we said before was, hey, that seems like a really high acceleration, doesn't it? But you know, if you look at it, the time it takes us to get there is 7.66 seconds. 7.66 seconds. Let's put that 7,000 newtons on our free body diagram. And in fact, up here we had a free body diagram too, didn't we? You know, this really should be just a block. I mean, I shouldn't have drawn a car, but I'll call this my free body diagram. Shows the forces and everything else, not the frictional forces. We're going to get to those later on in the course, but it's just showing how we would lay these things out in a free body diagram. All right, so we've got 60 miles per hour. We know it takes 7.66 seconds to get there. That's not all that, I mean, that's not really fast. It's not like 0 to 60 in 3 seconds. I'm not even sure what car does that, but 7.66 seconds is pretty good to go from 0 to 60. You know, how far would we have gone, right? Let's be the engineer. How far would we have gone to do that? Would we have traveled a quarter mile? Would we have traveled a quarter mile to get up to 60 miles per hour? I'm telling you right now, that would be no. Excuse me. I'm going to have a little sip of tea here. And of course, I already know, and you are probably way ahead of me. So the original distance was 0 meters, plus my original velocity, 0 meters per second, right? Times 7.66 seconds. That's going to give us not much of anything either. But the last one, 1/2 times my acceleration, 3.5 meters per second squared, times the time that it took us, 7.66 seconds squared, right? And that's going to give us the total distance that we've gone. Now, if you think about it, 7.66 squared, that's already 58, right? Now, times 3.5, or really we could say 1/2 of 3.5, which is 1.75, divided by 2 is going to give us a 102, so about the length of a football field. So in the length of a football field, this car has gone from 0 miles per hour to 60 miles per hour. That's pretty fast. Of course, you know, dragsters go much faster than that, really. You know, I haven't really finished as an engineer figuring out everything to do with this. You know, when it gets up to 60 miles an hour, how much energy is it going to have? So energy at t equals 0 is going to be 0 joules. And energy at 7.66 seconds later, t equals 7.66 seconds later, it's going to have 1/2 times the mass, 2,000 kilograms, times the velocity squared, 26.82 meters per second, all squared. I hope you can see that square. That's not a, excuse me, that's not a squiggle. Yeah, I've been doing a lot of lectures lately. I think I've done like 20 lectures in 5 days. So My throat is finally packing it in. Now, let's add those up, though. 26.82 squared gives me a huge number, 719 times 1/2 of 2,000 is just going to be 1,000, right? So 719,312 joules, right? That's not a lot of energy. If you think about it, what's a kilowatt hour? That's what you pay for energy in, isn't it? A kilowatt hour. So 1 kilowatt, kilowatt hour. What do I want to multiply that by to get it to joules? Because what is a joule? A joule is a watt second, isn't it? So let's get rid of kilowatts first. So let's put kilowatts on bottom and 1,000 watts on top. Right? Because we want to get to watt seconds, a watt second. Because a joule equals 1 watt second, or energy equals power times time, or power equals energy per time, right? Does everybody remember that? So 1 kilowatt hour is actually a thing of energy. It's a unit of energy. Times 1,000 watts divided by a kilowatt. So let's get rid of the kilowatts there. And then let's get rid of the hours and turn them into seconds. So it's in the numerator, so we have to get hours, 1 hour in the denominator, and then 3,600 seconds. And so it's 3.6 times 10 to the 6 joules equals 1 kilowatt hour. So you can see that really here, 719, that's only about 1/4, right? Maybe I should say 1/5 of a kilowatt hour. And that's our unit of electrical energy that you pay for. Now, if we've got that, and we know that this is going to be expended in 7.66 seconds, what's the power of that engine in that car? Well, wouldn't it be the energy per unit time? 719, 312 joules divided by 7.66 seconds. That's right. That's what the power is. The power is 93,905 watts. Excuse me. Late at night. So 93,000, yeah, I guess I got to do them in the morning. 93,905 watts. But how many watts are in a horsepower? Well, it's 743 watts in a horsepower. So wait a second, let me do this again. 93,905 divided by 743 gives me 126.4 horsepower. So you can see that this really, I mean, this is a car that's got a 126 horsepower engine. There's some cars, a lot of cars that have that. A lot of cars that accelerate to 60 in about 7 or 8 seconds. If those cars were accelerating straight off the bat and had great friction with the road, they would do that in about the length of a football field. Yeah, they'd be up to 60 in about the length of a football field, because we've done the analysis of all of that right here, haven't we? Just using our understanding of engineering, our free body diagram to sort of lay things out, just like we did the coordinate system transfer up there with no problem. Okay, that is our whatever lecture, and we'll be moving on to the next one, but not till tomorrow morning, most likely. All right, see you there.